For those listening, I'm David. Those who are here, I'm still David. This revision seminar is for Maths 1A, and it's about derivatives of inverses and how the chain rule interacts with that, and also derivatives of integrals. Okay, so in the middle of Maths 1A, I mean, a large amount of Maths 1A is about integration. So you've got upper and lower sums, and you've got techniques of integration. And then in the middle, there's this bit about logs and inverse trig functions, and there's all these derivatives. And really, one of the only reasons you're talking about derivatives at that point in the course is so that you can do integrals later on. So you need the derivatives of your logarithms, and you need the derivatives of your inverse trig functions in order to be able to integrate certain key functions. And so that's why they are there. But you need some theory as to how those things work in order to, because mathematicians like to show you the theory. So that's what that bit's about, and that's why it's there. And so that's why I like to talk to you about why something is in the course. It's there for the purpose of coming up with the various things that you know how to integrate. Okay, so I'm going to do this in a slightly different order. I'm going to start with the actual ultimate answers that you need to know. Okay, so the first ultimate answer you need to know is the derivative of ln x. And actually ln, the absolute value of x, has the same derivative. So that's the derivative of ln x, it's 1 over x. And there's also some of the inverse trig functions that you're supposed to know as well. Can I ask, does your lecturer call it arcsine, or does your lecturer call it sine to the minus 1? Sine to the minus 1? Maple-TA and Wolfram Alpha will call it arcsine. But it's also known as sine to the minus 1x. Okay, so either one, doesn't matter. They're the two same names for, different names for the same function. The derivative of that is 1 over root 1 minus x squared. Excellent. And then arc cos, also known as cos inverse, its derivative is minus 1 over root 1 minus x squared. It's exactly the same as the derivative of arc sine, but with a minus. And then finally, arc tan x, which is also known as tan to the minus 1x, it's 1 over 1 plus x squared. So they are the derivatives of inverses that you're both supposed to just know. You're supposed to know how to derive them as well, but you're also supposed to be able to just remember them. Pretty sure your lecturer would probably be interested in you being able to know the inverse hyperbolic trig functions derivatives as well. But I could be wrong about that. I don't remember them off the top of my head, except for arc shine, which has a plus in this spot. But that's the only one I know off the top of my head. The other ones I'm not sure. So I'm pretty sure I'm going to say that I'm pretty sure that your lecturer doesn't want you to remember off the top of your head the derivatives of the inverse hyperbolic trig functions. But he does expect you to be able to deal with them if you're ever asked to prove one of them on the fly. Okay, so these are the ones you're supposed to just remember. Okay, and knowing that these are the derivatives means that when you're asked to find the derivative of something that involves those functions, you are able to use this formula straight up without having to prove that it exists. And so I'm going to do that example first before I move on to the bit of proving why they work. Okay. What about y is equal to arc cos x squared? I don't have to do any of the proof to do the derivative of this unless I am asked specifically to do that. I can just use the formulas that I'm supposed to just know. And I'm supposed to use the chain rule for any situation where there is something inside another function where I would normally expect there to be an x. So I have a mantra that I say to myself every time I see a derivative that's got something in the spot where I would expect there to be an x, and I say, I would know what to do if it's an x, but it's not an x, so I'll have to multiply by the derivative of what's inside. So, I would know what to do if that was an x. If it was just arc cos x, the derivative would be 1 over root 1 minus x squared, with a minus there. That would be the derivative of arc cos x. But it's not an x, it's an x squared. So I'm also going to have to multiply by the derivative of what I put inside those brackets. And that's it. And that is as simple as, and that is all the working that people writing your first year maths exam want for a question like that. You don't even, I mean, they probably don't want the arrow there, but they won't mind if it's there. So you're allowed to simply, simply relative to proving it, using the proof, you're allowed to just write down the formula for the derivative of arc cos, put an x squared in it, and then also multiply by the derivative of x squared. Okay, you do not have to do anything more complicated than that. It's the chain rule. Okay, the chain rule always works that way. It doesn't matter how complicated the function is. So just as another example so that you can see something quite ridiculous. The chain rule says that if that was just an x, I know what to do, and so I will do what I would normally do if it was just an x. It's 1 over whatever all of that is. And then I put the stuff that was there, and then I have to multiply by the derivative of what I had. So 3x squared plus 2, derivative of e to the x is e to the x. Okay, so that repeating that to myself every time is what helps me deal with the chain rule. Now, some of you might be really used to using the chain rule, and so that's all good for you. But I do know that if the chain rule is still a really recent thing that you learned, anything that you learned recently has the chance of becoming interfered with anything new that you're trying to do. So when you try and do anything new, something else that you used to know how to do will temporarily be unavailable to your brain. Okay, and for some people it's the chain rule. When they're trying to differentiate trig functions or ln's, they stop suddenly being able to do the chain rule. So be aware that you have to really know the stuff that comes before, and be aware that anything might at any moment suddenly become unavailable, so you need to know it really, really well, so that that's less likely. So don't feel bad if something you used to know how to do you can't do, but do be aware that it does sometimes happen. Okay, that is using the chain rule with these functions, and that is the extent of all there is to it. Great. But if you want to prove that one of them has that inverse, then there is a way of going about it that uses a specific rule. And it goes like this. There are two versions of the derivative of an inverse formula. Okay, so there's one that goes like this.
it goes that if y is equal to fx, right, then dy on, just a second, yep, dy and dx is equal to 1 over dx on dy.
That is version number 1. Usually there's an f inverse here. I'll make it f inverse. If y is equal to f inverse x, dy and dx is 1 over dx on dy. It doesn't matter whether y is equal to fx or y is equal to f inverse x, it works. The point about it is that actually if y is equal to f inverse x, that means that f of y is equal to x. So if y is f inverse, if I do f on both sides, I'll have f of y and f inverse of x. And the f inverse will cancel each other out because that's what they're designed to do. And I will produce fy equals x. And so when I look at this dy on dx, it's the derivative here. And this dx on dy is the derivative here. So that is version 1. Version 2 is that dy and dx, which is equal to f inverse dashed x in Newton's notation, is 1 over f dashed f inverse. Like that. These are the two different versions of the inverse of derivative of an inverse. One of them uses Leibniz's notation with the fractions dy and dx, and the other one uses Newton's notation with the dashes. They are the same thing, but one of them is more useful for doing proofs and the other one's more useful for doing calculations. So this one's good for proofs. And this one's good for calculations. And it's good to know which one's useful for. They're two whenever you have more than one representation of anything, usually one representation is better in one situation and another representation is better in another. Just like representing a fraction as a fraction is useful for when you're doing algebra, but representing it as a decimal is much more useful for chucking it in a computer. So it's the same deal. One of these is better for one situation and one of them is better for the other. So I'm going to use the calculation situation first and do an example of how that's often used. Okay, suppose f of x is a function. It's supposed to be a differentiable function, but I'll leave that bit out. Suppose f of x is a function such that f of 1 is 3, and f of 2 is minus 1, and f of 3 is 0, and f dashed just give me a second. Of 1 equals 5, nope, sorry, minus 5, f dashed of 2 equals 2, and f dashed of 3 equals 1. Okay, so we've got this information. Fx is a function such that all of those things are true. Find f inverse dashed of 3. That's my example problem. It's a classic assignment question. Not so sure about exam questions, but it's a pretty good exam question. The clue that the Newton's version is the one we should use is already written in the dash. Okay, and also we don't have a formula for what f of x is. Okay, we just have some of its some of its values at certain points and its derivative at certain points. But what we don't have is the actual formula for it. So we can't differentiate it using the formula. So we can't figure out that dy and dx as a formula, so we're going to just have to use it at one specific spot. But the formula for the derivative of an inverse says that f inverse dashed of 3 is 1 over f dashed of f inverse of 3. That's what the formula says. So it says that to figure out the derivative of the inverse, I need to first figure out the inverse and then chuck it into the derivative of the original function and do 1 over that to figure out the answer. So I need to first figure out what f inverse of 3 is, and then I need to figure out what f dashed of that answer is, and I need to go 1 over that answer, and that will be the final answer I'm looking for. So let's see. Can anyone tell me from the information here what f inverse of 3 is? Yep. It's 1, yes, because f of 1 is 3. So f of 1 is 3, and so therefore 1 is f inverse of 3. Because the point is that f takes a 1 and produces a 3, but f inverse does the opposite. It takes a 3 and produces the 1. That's the whole point of f inverse, is that it does the opposite of what f does. So anything that comes out of f, if you put that back into f inverse, it produces the input from f. And so I know what f of f inverse of 3 is. So f dashed of f inverse of 3 is the same as f dashed of 1, because f inverse of 3 is really 1. And f dashed of 1, according to my list, is minus 5. And so finally I can sub this answer back into there. F inverse dashed of 3 is 1 over, which is minus a fifth. And that is all there is. Note that from the information I have here, I can't actually figure out what f inverse dashed is at any other point from the information I have in this question. I can't figure out what f dashed inverse of 1 is, because nothing came out to 1, so I can't find f inverse of 1. And I can't figure out, I could conceivably possibly figure out what f inverse dashed of 0 is. Yes, I could have figured that out, because I know what f inverse of 0 is, which is 3, and I know what f dashed of 3 is. So I could have figured out f inverse dashed of 0. That's the only one I could have done, because nothing else matched up nicely the way I wanted. Okay, so that's an example of using that number formula. It is not impossible, it's not impossible to use the dy and dx and dy version for that, and I think I might show you just to show where the dy and dx is fitting in with that. So let me just show you how that would have worked with the other version so that you can see how it's done if you prefer the other one. So let's let y equals f inverse of x. Okay, and that means that f of y is equal to x. And I know that dy on dx is 1 over dx on dy. Okay? So I know that f inverse dashed of 3, so of x, is dy on dx. That's what f inverse dashed means. It's the derivative of f inverse, which is dy on dx. And I know that that's actually 1 over dx on dy, which is 1 over f dashed y. So you see, this is, well, hopefully you see, this is actually where this formula is coming from. This f 1 over f dashed f inverse x is coming from this formula here, because we have f inverse dashed is dy on dx, which is 1 over dx on dy, which is f dashed y. And so we have f inverse dashed x is 1 over f dashed y. But the y is really f inverse x, so if you sub that in there, you get the same formula as the other one. So it's just, that's what I was trying to show, is how those two things were connected. But what this means is that when you have an x here, you need the matching y here. So we know that when
So we know that f of 3 is 1, which means that when y is 3, x is 1. So we have that dy on dx when x is 1 is the same as 1 over dx on dy when y is 3.
That's how you have to write it if you want to do it this way, which is just crap. So that's why I don't like using this version when I've got numbers, because it's just insane. You don't like it at all. But that's the idea behind it. So, yeah, it's awful. dy on dx when x is equal to 1 is crap. Yeah. X is equal to 3, y is equal to 1. I've been doing this too long today. This is why exams are only 2 hours long. Because, when you've been doing revision seminars for 2.5 hours in the morning, you really shouldn't do another one in the afternoon. That's a bad plan. I'm just going to scrap this page and start again. Right. So we know that f of 1 is 3. Much better. Sorry, I had everything backwards. F of 1 is 3, which means that when y is equal to 1, x is equal to 3. And the reason that matches is because I've got f of y equals x. Everything's backwards. And so I have dy on dx when x is equal to 3 is 1 on dx on dy when y is equal to 1. But dx on dy is f dashed 1, which is minus 5. So that's the other way of going about it. Just to let you know that if you really want to do it with the dy on dx, you can. But also explaining why it makes much more sense with the dashes version. On the other hand, though, the dy on dx version works much better in a proof than the dashes version. And I'm going to show you that. Find dy on dx of arc shine x. Oh, sorry. A shine x. Not allowed to say arc for shine, because it's not an arc. Yeah, because you see trig functions go from angles, which are arc lengths around a circle, and produce numbers, but hyperbolic trig functions actually go from areas and produce numbers, and so it's not arc shine, it's area shine. So that's why you put an A there, which is probably why it makes more sense if you just put an inverse. But there you go. Hyperbolic functions are cool. They're really totally awesome for many, many reasons. I love them dearly. And the day that last year when I realised that it was actually areas that made it work, the whole thing made sense suddenly, and my life was complete for a day before a new thing came up. But that made me very happy. So if I want to find the derivative of that, the best thing to do is to start with y equals. Did it again. Okay, A shine x. So note that I did not say let y equals shine x. I literally just said this function here I shall call y, so that what I'm really finding is dy on dx. That's what I want to find. But the whole point is that dy on dx is really 1 over dx on dy. So what I need to figure out is dx on dy instead. So what I'll do is I'll do shine on both sides. So start with this one. I'll do shine on the y, which produces shine y. And shine of A shine is just nothing, so that's just x. It's just the do nothing function. And so I have that x is actually shine of y. And so dx on dy is cosh y. because the derivative of sine is cosh. Awesome. And so therefore dy on dx would be 1 over cosh y. Sweet. But the whole point is that I wanted dy on dx to all be in terms of x, so I'm going to have to sub in the y equals sine x into that. But cosh of sine, no, I'm not going to do that. What I'm going to do is I'm going to use an identity to transfer my cosh y into something in terms of x. So I'm not going to just sub in y equals a sine x into there, because that's not helpful to the reader.
So we're going to do this. We're going to say, well, just a second, I do know a relationship between cosh y and sine y. I know that cosh y squared minus sine y squared is 1.
Now if this was cos and sine, there'd be a plus in the middle. But cosh and sine have a minus in that spot. And in order that you have them the right way round, it's not sine squared minus cosh squared. In order to have the right way round, you need them in alphabetical order. C comes before S in the alphabet. So that will arrange for the minus to be in the correct spot. Okay, so C is before S in the alphabet, so cosh squared minus sine squared equals 1. It works for me. If you have a different method for remembering where the minus, which way around it goes, go for it. But that's how I do this in alphabetical order. And so cosh squared minus sine squared is 1, and I know that sine squared is x squared, because sine y is really x. So cosh y squared is 1 plus x squared, and then cosh y would be, and it can't be both plus and minus, but we're in luck because cosh is always positive, so I don't have to worry about that. Because cosh is always positive, we're good. We just take the positive square root. And so therefore, dx on dy is really root 1 plus x squared, because it was cosh y. And therefore dy on dx is really 1 over root 1 plus x squared. See, told you, it was the same as the one for sine, but with a plus instead of a minus. The classic, I should point out to you something. When you do this with an ordinary trig function, there's this interesting bit that happens just here when you choose the plus or minus. So I'm just going to do that for you to see where it happens so that you can see what happens to it. Let me do it with sine so that you can see what happened at that spot. I'm going to skip a bit of the working though, and you can look this up. This should be in your lecture notes. I'm pretty sure it's in the lecture notes, so you can look up the bit that goes in between. But I would like to show you what happens as you go. Oops, sorry. Arc sine x, you'll get sine y equals x, x equals sine y. I'm not going to skip the middle apparently, I can't do it without actually doing it. So you'll get to this stage, you'll get exactly the same bit, cos y squared plus sine y squared equals 1. Same thing will happen. Okay, so what I did at this stage, I did the same trick. I did y equals the thing that I had. I did sine on both sides. I flipped it over so I could differentiate it. And I'm just starting on my trig identity. But sine is really x in this context. And here I am here. And so cos y is plus or minus root 1 minus x squared. Here's the problem. How do I know whether it's the positive one or the negative one? Because it can't be both, or it wouldn't be a proper function. So I have to choose one of them. And I have to choose one of them based on this vital piece of information. Y is arcsine x. And if y is arcsine x, then as an angle in the unit circle, that means that y is here. Because arcsine produces angles between minus pi on 2 and plus pi on 2. We had to restrict the domain of sine in order to produce its inverse. And so that's what we restricted the domain of sine to in order to produce its inverse. It produces... so now, I was only allowed to do arcsine if the outcome comes between minus pi on 2 and plus pi on 2. So this is the domain, so this is the range of arcsine as angles, which also happens to conveniently be the place where cos is positive. Because cos is the x-coordinate of a point on the unit circle, and the x-coordinate's positive over here. Wow, it's almost as if we planned it that way. So you'll notice that arc cos produces its answers in the place where sine is positive, which is really useful. Okay, so arc cos produces its angles between 0 and pi, which is up here, which is where sine is positive. It's really convenient, and they've chosen it that way for a good reason. And so we can say that actually cos y is positive 1 minus x squared, since y is arcsine x, and so is in the first and fourth quadrants. And so therefore, dx on dy is root 1 minus x squared, and so dy on dx is 1 over root 1 minus x squared. So that's the proof that arcsine's derivative is 1 over root 1 minus x squared. I'm pretty sure that no one will care if you forget to do this bit just here, but people will be most impressed if you do. And it's nothing like impressing your marker. It makes them feel happy, and happy markers are generous markers. Okay, so that is proving that that inverse functions work. And I have one more proof to do, just to show you how it's done. Actually, no. Yes. Prove that derivative of e to the x is e to the x. This is a great proof. I love this proof. The reason you can prove this is that probably when you first saw the function e to the x, it was defined as just here it is. There's this random number which happens to have the property that the derivative of the e to the x function is 1 at the origin. And then from there you defined ln as the inverse of e to the x. But here in Maths 1a we've done it the other way around. We've started with ln x as defined to be the integral of 1 over x, and then we've defined e to the x as the inverse of ln x. And so here in Maths 1a, the proof that d on dx e to the x is equal to e to the x uses the derivative of ln x, because that's how we did it in Maths 1a. So we're going to use the derivative of ln x to prove this. So same deal, let y be e to the x. And we're going to do exactly what we did with the arcshine and the arcsine, the ashine and the arcshine, with the other functions that we previously mentioned. And we're going to do the inverse on both sides. So we do ln y equals x. So we do ln of y, and ln of e to the x is x. And so we have x equals ln y. And dx on dy is therefore 1 over y. Awesome. But y is e to the x. So we'll sub that in. And so therefore dy on dx is e to the x, because we'll do 1 over e to the x, which is e to the x. Brilliant! That's the proof. Sweet. Okay, you don't have to do any of this playing around with pluses and minuses because e to the x is positive anyway. It's all great. That's one of my favourite proofs. It's like, nothing up my sleeves. Bah! There we go. Okay, so that's using the derivative of an inverse to prove that the derivative of e to the x is e to the x. But it all hinges upon the fact that in Maths 1a we defined ln x to be the integral of 1 over x. Okay, if you're in a different course where the definition of e to the x was something different, then the proof would be different again. But luckily you're in Maths 1a, and so now you know what that looks like. Okay, so they are. What have we done? We've done using the chain rule with these derivatives of inverses. We've used we've shown how to do some proving with derivatives of inverses, and now that's good. That ends that bit there. The next thing I want to talk about is differentiating integrals. Does anyone actually have anything that they want to ask about derivatives of inverses before I move on? Because I would hate for you to come all the way into uni in SWAT week and not ask you a question if you have one. Cool. Okay. There is a Maths Learning Centre is open, so feel free to go there as well to talk to us about it if you don't feel comfortable saying it in a big crowd. So, derivatives of integrals. The fundamental theorem of calculus says that an integral is an antiderivative. Okay, so just so that you know, the fundamental theorem of calculus says that the integral from a to b of f of x dx is says that, as which is shorthand for this. Okay, that is the fundamental theorem of calculus, but it's not quite the whole fundamental theorem of calculus. The fundamental theorem of calculus says that this is true as long as the derivative of f, big F, is little f. So in words, as long as capital F is an antiderivative of little f. Okay, that's the fundamental theorem of calculus. So what the fundamental theorem of calculus says is that when you attempt to do a definite integral, what you're really doing is the opposite of differentiation. You are undifferentiating this little f to produce this big F, and then you do the subtraction and that's the answer. That's the fundamental theorem of calculus. The reason it looks so unimpressive is because it's fundamental. Fundamental theorems never look impressive. They're so fundamental that you didn't even realise you were using them most of the time. Okay, that's why it doesn't look impressive. There is a theorem that comes before the fundamental theorem of calculus that sometimes lecturers mean when they say fundamental theorem of calculus. So in your textbook, if you've ever looked at it, it's not really necessary to buy the textbook in first year, but if you've done that, and if you've looked inside it, you will note that it actually has in your textbook the fundamental theorem of calculus part 1 and the fundamental theorem of calculus part 2. This is the fundamental theorem of calculus part 2. So the other fundamental theorem of calculus is, so this says that to integrate you need to do the opposite of differentiation. So it's basically telling you how to integrate a derivative. It says if little f is already the derivative of capital F, then this is how to integrate it. So this is integrating a derivative. But the other half of the fundamental theorem of calculus tells you how to differentiate an integral. Okay, so this is saying little f is already a derivative of capital F, and this is how we integrate it. Now we're going to say, here is a function which is an integral, how do we differentiate it? So the other half of the fundamental theorem of calculus is this. It says that if f is already the integral of some other function, and just so we don't get confused about all the x's flying everywhere, we will use a t in this spot. Some people use an x down below and up the top, but that can be a bit confusing when you're subbing an x in for an x, but it's already an x, so I'm just going to leave it like that.
So if a function is already an integral, then the derivative is the thing that you integrated.
So that's the other half of the fundamental theorem of calculus. In your notes, it's not actually the fundamental theorem of calculus. It's just the theorem before the fundamental theorem of calculus. It doesn't have a name. It's like theorem something point something. But you're not expected to remember the formula, the theorems by number, only the ones with names. Right, so this thing here is how to differentiate an integral. It says that if a function is already a definite integral of some other function, then its derivative is the original function you first thought of. So here is an example of how that works. And I'm going to give you several examples of how to deal with this when it's not exactly this situation. Okay, so my first example is just the basic example. Okay, f of x is the integral from 3 to x of sine e to the t dt. Awesome. Well, I don't need to know how to integrate this function because... Okay, so this is the question that we've been given in our exam or whatever. F of x is the integral from 3 to x of sine e to the t dt. Find f dashed x. So note carefully the goal here is to find the derivative of this function. I do not need to know what this function actually is. I don't need a formula for this function, I just need a formula for its derivative. And that's the clue that you're supposed to use this derivative of an integral thing.
So f dashed x is simply sine e to the x.
Yay. But, key point to note, it makes not the slightest difference what this number here is, as long as it is a number and not a formula involving x. It could have been 31, and it wouldn't have made any difference because the derivative would be the same. So it's not to say that the integral from 3 to x of that is the same as the integral of 31 to x of that. It's to say that whatever those two integrals are, they have the same derivative. Which means that as functions they differ by a constant. Okay, so the integral from 3 to 31, which is the difference, that's my plus c when I do an integral. So I'm just going to draw a picture here. Here's my 3, here's my x. This is actually probably not bad, a picture of what sine e to the x is, because it should have a little wiggle in it because of the sine. And this area here is capital F of x. As the x moves, capital F of x gets bigger. So the x moves a bit, the capital X will get a little bit bigger. The x moves a bit further, the capital X will get a little bit bigger again. And if the derivative is the rate of change of that slice of area compared to how quickly x is changing. All right? But if I had started at, say, 31, then this area here is a totally different area to that area there, but the leading edge is moving at the same speed. The leading edge of this function where I'm integrating is getting the areas being added on at the same speed no matter whether I started at 3 or 31. So what we're interested in here is the speed at which that area gets added on, not what the area is currently, and that's why the derivative is the same. And the other thing is that, look, this f of the one from 31 to x is this plus c. That's my, plus c. There, and that's why it differentiates to give 0. If none of those explanations convince you, I can give you more in person if you want to talk to me or one of my staff. Yes, but that's the reason behind it. It doesn't matter what that number is, as long as it is a number and not a function of x. And therein is the problem. What do you do if it's not an x, but it's something else? just a second, I had a mantra for that. I know what to do if it's an x, but it's not an x, so I should multiply by the derivative. Okay? So any time you're in a situation where you have to differentiate and what you see, you would prefer it to be an x, but it's not, you will pretend it is an x, and then you'll multiply by the derivative.
So this is the example of using the chain rule.
Okay? So this integral here, well, I would know what to do if it was an x. If it was an x, I'd just put the x there. But it's not an x. So the chain rule says that I should multiply by the derivative.
So f dashed x, if that was just an x, the x would go here. It's not an x, it's an x squared, so I have to multiply by the derivative of x squared.
That is all there is to it. You do not have to do anything else. You just have to write that down. And so we get 2x root 1 plus x to the 4. Now that may seem like magic, but that's the point of the chain rule. It is, well, it's not really magic. It's maths, which is better than magic. So that's what the chain rule is for. It's specifically for dealing with this situation, for the situation where you would know what to do if it's an x, but it's not an x, so you multiply by the derivative of the thing that is there. That is exactly what it's for. One of the ways that I have of helping people understand this is, I really prefer a highlighter. This will do. Look, all of this all of that stuff is just a really fancy name for a function. You know, it could be called sine x squared. Okay? And you know what to do if it was sine x squared. You'd go cos x squared times 2x. It's just that this is the name for the derivative. So you're used to functions just having random names, right? We've got this random name called sine and it differentiates to give this other random name called cos. Same deal. Here is this random name and it differentiates to give this random name. And if I don't have an x, I just times by the derivative.
So that's the idea behind it. It's just that included in the name is what it tells you what to do, which would be totally awesome if that was the name of sine and cos.
You say, yeah, instead of having
having cos x, you had the function that differentiates to give sine x.
Right? That's the name of cos x. Okay, and that's what we've been told. We've said the function that differentiates to give root 1 plus x squared, but with x squared in it instead of x. That's what we've been told. Okay? So this is just a long, long name for a function. Right. So what do we do
if the x is down here? Nice function.
A really good integrable but no formula for its integral function. So, we know what to do if there's a number here and an x here. And our normal chain rule thing only works if there's a number here. So I need to turn it into something that I do know how to deal with. Just a second. If I want to switch them, which is what I really want to do, because I prefer the number to be at the bottom,
I can just minus it.
When you switch the top and bottom limits of an integral, you just minus the integral, because you're doing the integral backwards, so it comes out to a negative answer. And now I can integrate it.
The minus will still be there because that's what happens when you integrate something with a minus out the front. And the derivative of this is, well, that. Damn, it's supposed to be t's. The statics lecturer has corrupted me. No, sorry, dynamics lecturer. That's next semester. The dynamics lecturer has corrupted me. I used to like quail in horror when I used an x in the limit and in the integral as well. And now I just don't bat an eyelid because I'm so used to it from physics. Okay, so that's the deal. If it's the wrong way around, we'll just switch it because you're allowed to do that with integrals as long as you put a minus out the front. And my final answer, my final question, T tan T. I like T tan T. Again, all right, I would know what to do if there was a number in this spot. And if there was a number in this spot, cool, then I could do my chain rule and that would be great. But there is not a number in this spot. Now my little mantra only works if I'm replacing an x with something else, and there was not an x in this spot. So somehow I need to turn this into something that has a number in that spot. Let me think about what this means. I'm not really drawing T tan T because I don't know what that looks like off the top of my head. Here's a function. Here is x squared. And here is x plus 1. And my function is the area between them. So what I would really like would be a number. You know, I'd really prefer this to be a number here. So I'm going to construct it out of one that has a number because I'm going to mark this point here. And I'm going to say my function is this integral from here to here minus this bit here. And that would leave me with a bit in the middle. Sorry, that was bad writing. But I'm going to have the integral from here to here minus the integral from here to here, which will leave me with this integral in the middle. Very nice. And now, there's a number at the bottom of both of them. And I know that the derivatives can be done separately. I can do the first bit and then minus and do the second bit, and that'll be all good. So f dashed x. So let's see, the derivative of this, if it was an x, I'd put the x in this spot, where both of these t's are. But it's not an x, it's an x plus 1. And I have to times by the derivative, which is 1. And over this side, if it was an x, I would put an x in both of these spots. But it's not an x, it's an x squared, so I have to times by the derivative of the inside. You don't have to do it for both of them separately. Don't worry about that, because they both produce this same one. So I have x plus 1 tan x plus 1 minus 2x cubed tan of x squared. It's awful, but you know, it wasn't going to be pretty. This was not a happy, pretty function. So it can't have a happy, pretty derivative. And technically, if I was wanting to punish myself, or the person writing my exam wanted to punish me, I could now differentiate it again. I could find the second derivative. Because now it's just ordinary differentiation, if I really wanted. And I'm going to do that just to point out all the other rules of integration, of differentiation. Ready? This bit here is a product. It's two things multiplied together, so I'm going to have to do each derivative separately. So the x plus 1 will differentiate to give a 1, but I'll keep the tan of x plus 1. So I differentiated this bit and I kept this bit. And I will keep the x plus 1, but I will differentiate the tan of x plus 1, which will give me sec x plus 1 squared. But because of the chain rule, I'll have to times by the derivative of that, which is 1. That was the product rule for the first bit. Second bit, differentiate that, which will give me the 2 will still be there, 3x squared. Keep the tan x squared. So that's the first bit. And now I will keep the 2x cubed and differentiate the tan x squared. Now the derivative of tan is sec squared, but it's not an x, it's an x squared, so I'll have to times by the derivative of that.
Sweet. Awful, really, but there you go.
So this is not going to get any prettier by simplifying it.
There you go. That's the second derivative. Note that I didn't have to use any fancy derivatives of integral things to do that second derivative because it's just a brand new problem. Here is a crazy, crazy function, and now I'm going to do this the next derivative of it. Right. Just thought I'd point that out. So that is derivatives of inverse functions and derivatives of integrals. Did anyone have anything to ask about generally that area before I move on to other requests? Yes?
When you did the integral of the x squared to the x plus 1, you assumed that the x squared was smaller than the x plus 1. Will that always...
Yep, let me say that for the people who are listening. So the question is, I assumed that the x squared in my picture was less than x plus 1. Is that okay? Is that always true? It's not always true. Obviously, if x was, say, 7, x squared would be more than x plus 1, but it doesn't make a difference to the integral. Because even if it's the wrong way round, I'll just get a minus for the answer I was looking for. So it is actually, I could have just as easily have done this. And the 0 could be here. And then it would be from 0 to x squared minus from 0 to x plus 1. The answer would have come out the same because this integral here is actually the integral from x plus 1 to x squared, which is minus the original integral because it's the wrong way round. So the fact that my integral, maybe the x squared is bigger, but that means that my integral is the wrong way around to begin with. So I flip it over and it becomes a minus, and then I do that, and all the minuses cancel and it all turns out the same anyway. So you can actually completely ignore what the actual sizes of these numbers are, because normally you just put that diagram on your scribble paper and pretend that you didn't use it. You'd say, I was really clever and didn't use a diagram, even though, of course, we all know that using a diagram is way more intelligent than trying to not use one. But yes, normally you put this diagram on the scribble paper so as the person who was reading it didn't get confused as to which order the x and the x plus 1 was in. Of course, if x was a small number, like a half, then it would be true, so it's okay. All right. Cool. I'm going to stop the recording and